Today we will see some branching algorithms. I'm sure all of you have seen some form of branching algorithm. So in early parameterized complexity, when like first 10, 15 years, 10, 12 years, we did following kind of branching. So let's fix vertex cover. Okay, you know all the problems, I'm not going to tell you. So the history tells us that the first published algorithm, which nobody knew, was some f of k times poly in n, okay, using GMT, graph minor theory. Okay. So this was the first algorithm known. Then there was an algorithm by Bus kernel, and they gave an algorithm because you have k square vertices, so it's like k square choose k, which is roughly k to the power big O of k. Okay. And then Papadimitriou and Yanakakis they were making defining a new set of class called log SNP and so on and so forth, and they needed an algorithm for vertex cover that ran in time c power k. Because what was their objective? Their objective was to show that the log n, so is there a vertex cover of size log n is in P or not, okay, is does G has vertex cover of size at most log n or not, whether it's P or NP, right? Clearly they could not have shown this problem to be in NP, because of course I can solve this problem in n to the n choose log in time, and like I'm avoiding some polynomial factors, and assuming the well-known complexity hypothesis, you do not expect that quasi P or quasi polynomial time is equal to is like a problem which has a problem pi that has quasi P algorithm is NP complete. We do not expect this. So the only thing which is possible is that either this problem is in polynomial time, like for example graph isomorphism cannot be shown to be in, cannot be shown NP complete anymore, right, because it already has a quasi polynomial time algorithm. Problem could have a sub-exponential algorithm and it still could be NP complete, but if you have a quasi polynomial algorithm, you cannot show that problem to be NP complete. Okay, and clearly if I am looking for log n size vertex cover, log n size independent set, log n size dominating set, we always have trivial algorithm of this form. So there is no way I can show that the problem is, and that is why they were trying to define this class called log SNP, log VP or some such thing, and then they came up with this C power k algorithm, and their algorithm was slightly different. They said, okay, fine, I am looking for a k size vertex cover, let's find maximal matching or maximum matching, whatever it is, say max matching. If it is more than k, say no, so this is less than k. Now from every edge you at least need to pick one vertex, okay. So you decide either this vertex goes or this vertex goes or both vertex goes, right. So how many choices do we have? 3 power k choices. But once we have made these choices, what is there? You have a set of vertices which you cannot pick, and what is left outside is an independent set, because any vertex here is an independent set. So if you cannot pick these guys, you have to pick all their neighbors, right, and then you are done. So in 3 power k choices I can solve this problem in FPD time, right. So for every edge I guess whether this vertex goes, and you only have 3 choices, you don't have 4 choices. What do you mean? It's not that you cannot pick both, you have to pick at least one. So either you pick this or you pick this or you pick both, you make such choices, and so that will give you 3 power k choices, and for each choice look at the vertices which you have not picked, that is a vertex cover of the graph. You delete everything, that's a vertex cover of the current graph because it was a maximal matching, right? Then you just pick their neighbors. So this was a 3 power k algorithm in 90 is 3. Okay. And then someone observed this 2 power k algorithm. And there are like these big people. And then people observed that there is a 2 power k algorithm given in the textbook, prehistoric textbook by there's a book by the design and analysis of algorithm, I think, of algorithms. There are 3 volumes by Kurt Mulhern. Okay, so in that he actually gives 2 power k algorithm for vertex cover as a coping mechanism to NP completeness. And this book is from 1983. Okay, so this is a prehistoric algorithm. So all I was trying to tell you that as simple as it looks, this idea now, it took people 10-15 years to come up with this idea of branching. That's all that I was trying to tell, even for the vertex cover. Like, and these people are big people, right? They could see 3 power k algorithm, but they didn't see 2 power k algorithm. Right? And you can find it's solid their paper in JCSS or something. Okay, good. So do you know a 2 power k algorithm for vertex cover? Anybody?
Take any edge, this or this, you will not branch on them.
Excellent, right? So we have a G and comma K. I pick an edge UV. And now you will say why I get annoyed. Okay? But anyway, but it's not ended, okay? G minus U, K minus 1, G minus V, K minus 1. Yeah, correct. Very good, excellent. But that is where my question starts. I know everybody knows this. Okay? In this, then you just keep quiet. I mean, otherwise, others people will not understand this. Okay? Why did we not branch G minus UB K minus 2? Right? Who has told us? Look at the Papadimitri's algorithm, right? He was picking an edge and he is saying that either you will go into the solution or we go into, or both. Definitely, none does not happen. So in one branch, K minus 1, K minus 1 and K minus 2. Why are we not doing this? Why are people telling you this? Oh, hey, do this, do this. Why? Do you get my question? Why are we not considering this? If at all we have to be exhaustive, like we have to, look, so-called decision, look, suppose I want to prove that this algorithm is correct. A, how do I prove a branching algorithm is correct? So let's write down like what all things we need. A, how do we show my branching or recursive algorithm is correct? Right? Because the moment you try to show this, you will understand why we need something or why we do not need something. We all assume that, yeah, this is true. But suppose look, the reason why I emphasize here, because maybe here you hear 10 times and hence you start believing that, yeah, this is correct. But suppose you encounter a situation where, and we will encounter lots of situations where it would not be apparently clear that this algorithm is correct. You understand what I am saying? Here, I mean, you have heard this like last 1 year so many times that we have believed that this is correct. But have we bothered to at least make our hands dirty once and prove why it is correct? Because for me, there could be a solution which contains both U and V, and we are not considering that case. Why? It's just a matter of like food for thought. It's nothing amazing. But if you have an understanding of what is happening, it is much easier to design branching algorithms yourself. Do you get my question?
So we are not deleting V. So when we are taking U into the solution, we are not deleting V from the graph. So we can later, if there is an edge involving V, we can branch on that as well, and V and U can both go into the solution.
Okay. So let's, rather than, what is the meaning of this branch? Let's try to ask ourselves, what are we trying to achieve here? Right? What is algorithm trying to tell? He says, hey, so suppose I had a VC, like some procedure, vertex covered, which takes a graph and parameter k and returns something. So what would I have said, right? So if I would have written, so let's write VC of g comma k is equal to suppose it returns yes or no for now. VC of g minus u comma k minus 1 or VC of g minus v comma k minus 1. This is what it is, like it's or. Like if any of them is correct, then I return it's correct. Like for now, so for now my VC of gk is some kind of boolean, okay, it's boolean, right? I wrote this, but let's ask ourselves, what is the meaning of this? What is it trying to check? It is trying to check among, does there, like in this graph, it is trying to check over all solution of size at minus k minus 1, and clearly it does not contain u, right? So let's make a family, okay? So I am going to try to tell here, I am going to associate a family here. So what is my family of solution? So I am going to call family of solution for g minus u, okay? Family of solution of g minus u is basically all x subset of v g minus u, okay, mod x is less than equal to k minus 1 and x is a vertex covered of g minus u. This is the family solution g minus u, right? So basically this boolean guy is just trying to check whether this set is empty or not, right? Another guy, f solution other side g minus v some y subset of blah 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 blah, right? This is what it is going to check, right? So here I am checking whether this family of set is non-empty or not. In this branch I am checking whether this family of set is non-empty or not, right? If it is non-empty, then I will return yes. Suppose inductively this is what I try to prove. If this family is non-empty, I will return yes, right? And now how do you prove correctness? It is correctness by induction on k, right? You will have a base case. Now inductively it has a smaller value of k minus 1, right? So this guy will correctly tell us whether this set is empty or not, this family is non-empty. This guy will tell correctly. So by induction we know that this returns correctly, right? So and we know that if G has a vertex cover of size k, then at least one of these sets should be empty, because what is this set? What is this set? Here f solution of G is equal to f solution of G is equal to f solution G minus U union f solution G minus V. This is right. This is exactly U union V union. So like U is part of every solution which you are going to be here. So I have looked at my solution. There are some solution that contains U and there are some solution that contains V. Okay. So look at that solution. This is f solution G minus U. From there I have deleted U. What is f solution G minus V? It is all those solution that contains V. But I never said that they are disjoint. They could very well overlap, right? Okay. So whenever we are trying to do branching, our first thing is that we have a solution space and every branch is somehow trying to capture that solution space. Okay. So this is a very trivial way of branching, where I take a solution space from here, I take a solution space from here, and there is a way to get a solution space for the whole graph. But in branching, we do not have to follow this strategy. All I can make sure that, hey, in any branch this set is non-empty. Like when I go here, like by branching, all I want to ensure that you are not capturing all the solution, but all I want to do is that when I go here, this family of solution is non-empty, so that if there exists a solution, maybe I throw away some solution, that's perfectly fine. Maybe I say throw away solution, but I shouldn't be making sure, I should be making sure that if this was non-empty before, it remains non-empty now. If it was non-empty before, it remains non-empty. So all we have to make sure, if we understand this way, that when we branch, we can make choices such that it may not be preserving all the solution, but if there was some solution, then there is some solution that you have preserved in every branch, and that's all. Because if whatever the little set here it goes, if it is non-empty, by induction hypothesis it will return yes, right? By induction hypothesis it will return yes, and the exhaustiveness of here that every solution is of either this nature or that nature will allow you to prove the correctness. Okay, I will not go into more deeper than that, but that's a basic philosophy. And now you understand why we do not branch into UB, because all I decided that U goes into the solution. I never said V does not go into the solution, right? So if I look at my solution set, what is it? Look at all solutions that contains U. It might also contain solution where both U and V are present. So we have taken care of this. So if you look at from the solution space perspective, you will see that you are not missing out any solution, right? But if you are making a branching and you make one of the solution space empty, although it was non-empty before, then you are definitely making a mistake, right? So that is something which we always, this is what I mean by exhaustiveness, right? So whenever we are branching, if I wanted this family to be non-empty, all I need to make sure that my family is non-empty. Maybe I have pruned that set, that's perfectly fine. I do not have to, because this is what I say, I don't need to say for every solution. I said if there exists a solution here, then this branch will return yes, right? That's all that I care about, okay? And then you try to prove inductively everything. So this is exactly what happens, and this is why all these algorithms are correct, okay. Okay, fine. So basically what happened? So one basic objective is in this kind of algorithm in branching is that we come up with what is a basic principle. So basic principle is, here is the basic principle. Principle is coming up with a set, a subset of universe, okay, such that there exists an optimum solution that intersects A. This is all the principle that we maintain, right? Because if this is what it is, then I can say, hey, look, I branch in mod A ways and things will happen. And so at least you need this object to happen. And for us, for vertex cover, what was A? It was an edge, right? So if you maintain this, then all these invariants you can prove everything, right? So I will not go into the details of those, okay. But for completion, let me, okay. So by this we know vertex cover has 2 power k algorithm, okay. And how do we analyze that? We said, hey, if I really have to write running time of this algorithm, then there are several ways of writing this running time. What is this tk, like what is t of k? Tree, like time taken when the parameter value is k, time taken. No, it just intersects A. Look at edge. How do you know both will contain?
Okay, so this is not a solution set, this is a part of the obstruction.
Coming up with a set A such that there exists an optimum solution that intersects A. Okay. Time taken when parameter value is k. Okay. So like if I really have to analyze, I should be writing here k n because I have a k, right, and then I have to write, okay fine, look at this vertex cover, I have to write t k minus 1 and some n prime, t k minus 1 some n double prime plus some poly in n, because at that node we have spent some amount of time finding this edge and everything. So this is how a true recurrence will write. But notice, like, because all we care about is how the branching tree behaves with respect to k, I can forget this n prime from all over the places, right? So then ideally we should be writing still tk minus 1 plus 1 actually, because look, so what is this bounding? It is, so basically this is bounding number of nodes in search tree, number of nodes in search tree, this is what I am bounding, because I know that every node I am going to spend polynomial amount of time. So if I can bound the total number of nodes in my search tree, then my running time will be this times some poly in n, right? So if I look at this search tree, if I can bound the number of nodes in the search tree, then the running time of my algorithm will be total number of nodes in the search tree time amount of time we spend on each node, which is like polynomial. So this is this. But coming up with recurrence and solving this plus 1 is also a nuisance. So what we say is fine, I said come on, look at any binary tree, okay, look at any binary tree. Like by binary tree I don't mean full binary tree, a binary tree where every internal node has at least 2 child, okay. So here's the lemma. In every binary tree, number of internal vertices, binary tree, number of internal vertices is upper bounded by number of leaves, right? So if this you can prove, right? In any binary tree, number of leaves upper bounds, or maybe leaves plus 1, upper bounds the number of internal node. But what was this one counting? It was counting that internal node, no? What was this? I say here it is, number of number of nodes in this search tree plus number of nodes in this search tree plus 1 for this node, right? So now because we have this theorem, if I can forget this and come up with a bound, then all I need to do is multiply with a factor 2, which can be hidden in big O. So this is why, if you notice in branching algorithm, people only care about this and they forget about plus 1, multiplying with polynomial. It's like, okay, let's just count, let's bound the search tree, and not only that, let's bound the number of leaves of that search tree, multiply with 2, which is anyway hidden in constant, I don't care, and multiply with appropriate polynomial, that is the amount of time we spend on each node. Okay, any question? Okay, so okay, so this is basic principle A. Okay, basic principle B is branch towards EG case, which is same as saying can be solved, problem can be solved in polytime, solved in polytime on these cases. Okay, so this is my principle B. Okay, so now let's apply this basic principle to our vertex cover problem, right? So first we have to find a case where we can solve the problem in polynomial time. So for example, let's look at, here is a small lemma. Let G be a graph of max degree at most 1, then vertex cover of G can be solved in polytime. Do you agree? Right? So what is this? Either this is isolated vertex or matching edge. From every matching edge, just pick one vertex edge. So I can solve this problem in polynomial time on this, right? So when I get to a case where every vertex in my graph has degree at most 1, I shouldn't be branching, because now I can solve my problem in poly 10, because then I have reached to some easy case. Okay. So if I do that, then what happens? Okay, fine. So that automatically leads to following algorithm. What is the following algorithm that will leads to? So it will lead to the following algorithm, right? What is the algorithm? I am not writing some if k is less than 0, graph is empty, blah blah blah. I am not writing all those. Okay. Let V be a vertex of degree greater or equal to 2. Then branch on V. So now look at V and look at this. Why are we branching on V? Okay, we are branching on V because if you decide not to V, because the way the vertex cover problem is, if you want to cover a solution, you need to pick all these vertices into your solution, right? And this vertex has degree at least 2, right? So how will the algorithm look like? So algorithm is again like, so I write Vc of g comma k equal to Vc of g minus v comma k minus 1. This is I decided to pick this vertex in the solution, or Vc of g minus closed neighborhood of v comma k minus open neighborhood of v. Is that fine? Right, this is my algorithm. This is my recursive algorithm. Now you call, put some base case, but this is all that algorithm is. Okay, I don't know how to write programs, so I will not write pseudo code, but this is my recursive procedure. Okay. So now if I have to analyze this algorithm, as I told you, right, what it will be? T of k is less than or equal to number of leaves when the measure is k minus 1 plus number of leaves when, ideally this is what I should write, but I don't know what the size of n of v is. So what I have to write is less than or equal to actually max of this family of recurrence, where let's call this t is greater than or equal to this much. I know, right, that the neighborhood of v is at least 2, because we are branching on vertices of degree at least 2. So this, now you can prove that, think of this way, right, in, so which recurrence will be worse among all this? I mean, you can mathematically prove that. I mean, but intuitively, look here, I am anyway losing k minus 1, other I am dropping my measure much more, so the number of nodes in that search tree could only be smaller. So I can show that this is less than or equal to, this quantity is less than or equal to t of k minus 1 plus t of k minus 2, and if you do, this is like Fibonacci recurrence. Okay. Now how do people improve this? They will say, hey, look, why? I mean, I can also do this, let G be a graph of maximum degree 2, then also I can solve this problem in polynomial time, because it is nothing but cycle paths and all this. Okay, but now I will branch on degree greater than or equal to 3, right? But then I will get 3 here, because now this is 3 here, right? And then you will get some 1.45, I don't know the number. Okay. So then what people did in those 10-15 years, they looked at the case which is why this algorithm is hard, or why this algorithm is achieving the running time of this. They looked at the hard case and tried to analyze it much more finely and try to improve the running time. And this has been the history for lots of problems, like, I mean, vertex cover is not an exception for this. Okay. For example, 3 hitting set is one example. Like 3 hitting set obviously will have 3 power k algorithm, right, because there is a obstruction of size 3. D hit, so 3 power k. D hitting set will have d power k algorithm, but there has been lots and lots of improvement over here. Same for vertex cover. I don't even know what they write. I think the best known algorithm runs in time 1.27 something, which I do not know. Now you pick up any problem, no? Suppose if I give you clustered vertex deletion, CVD, what is the running time of this algorithm? What was the cluster vertex deletion? if after we delete these vertices, graph is disjoint union of cliques, and we gave a forbidden induced subgraph characterization of that, which we said that a graph G like is if and only if induced. What is the size of induced P3? 3 vertices, 3 power k, right? Okay. Suppose if I give you a split vertex solution. So split vertex, split graphs are those graphs which excludes C4, C5 and 2K2, induced 2K2. So what should be the running time of this algorithm? You're correct. You have to be live. Why 4 power k? What? How many vertices are here? How many vertices are here? Here? So, highest.
We want to take the highest.
You don't know if that is what you get an obstruction. You don't. You only know that one of them, right? So you have to put 5 power k, right? Because it's an obstruction, right? All you know that one of these vertices. So you always have to take the max. Okay. What about caudal graph? So caudal graph 4 power k. Okay. Feedback vertex set. Why 3 power? Okay, so max cycle to the power k, max length cycle to the power k. Huh? No, we are not assuming any fact, anything. So max length cycle to the power k. Okay, so someone has written a paper already in this class. Why caudal graph has 4 power k algorithm?
C4 is an obstruction.
Is that the only obstruction?
But because above is the obstruction, but this is a subset. Like, for all the other obstruction, you can find this structure.
Is it? So is your claim that a graph is caudal if and only if it contains induced C4s? Is this a caudal graph there? I'm a mean human being. Is it caudal graph or not? That's all that I'm asking the question. Is this a caudal graph or not? No. Then you don't know the definition of caudal graph. Yes? So what is the definition of caudal graph? At least you have to say that you either know or don't know, then I will define. If you say you know, then I will assume that you know and I will go ahead.
We cannot have an induced cycle of length 4.
Of length C4 or more. Okay? So this is?
Not a caudal graph because every cycle must have chords.
Okay, so this is not a caudal graph. Sure. Okay, good. So, right? So, but you claimed that if a graph is not caudal, which it is not, you just now said, it will contain induced C4, which I just don't see. This is what you said, right? A graph is caudal if and only if it contains, but this is a graph is not caudal. Please show me induced C4. Am I right? So, are you ready to take back your algorithm? Like, what should I write here? Huh?
Longest cycle is of longest induced cycle.
Longest cycle, same as FP.
Okay. Length of longest induced cycle. By the way, the best known algorithm for this problem is k power k. And we don't know whether there exists c power k or not. So, Okay, anyway, so you see there are lots of problems you can find and like co-graph, blah 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 blah. Okay, so I will not do any of these things. Okay. Okay. Let's look at vertex cover. Okay. Look at vertex cover. What is the property of vertex cover? What is this? It's independent set. So what is the property of this C? It covers all the edges. Definition. Now let's take feedback vertex set. F. Here I have forest. Can I say that it covers? That I know, but I do not want to care about cycles anymore in life. Cycles I cannot control. I somehow want to say that it covers all the edges, but of course it cannot cover all the edges because there are lots of edges here. So I want to relax this condition. Okay. So I am going to define a notion of alpha covering problems. A problem, say vertex deletion problem, let's call it a vertex deletion problem pi. Pi is called alpha covering if for all solution, if for all x subset of Vg, x is a solution, then number of edges incident to x is alpha fraction of total edges. Did you get my, so what is the property of alpha covering problem? You take any solution to the problem, then at least alpha fraction of edges they cover. Out of total edges, it cover all. So what is a vertex cover? What problem is this? It is one covering problem. Because it covers all. So alpha fraction, right? So fraction one covering. Can I say something like that for feedback vertex set? Yes, no.
E minus n minus 1 by E.
No, I want constant. Huh? Yes, no, maybe, could be. Do you at least get the question? What is the property of alpha covering problem? Property is if pi is an alpha covering problem, okay, then every solution covers that much fraction of total number of edges. If I can prove this, then this is a great. Do you see why this is great then? No? In particular solution of size at most k covers that fraction of edges, right? So if I randomly select an edge, what is the probability that it is one of the edges that is covered by these vertices? Right? And if alpha is constant, and then with probability half I can pick this, so this is a great randomized algorithm. So if I can do this, it will lead to a great randomized algorithm. We'll get there. We'll get there tomorrow, day after tomorrow. At this point of time, I just want you to absorb. Hello? Yes? Yes, calling from? Interested in? No, not now. I'm meeting someone from integrated at 1 o'clock. I'm meeting someone from integrated at 1 o'clock. Okay, bye.
So does that solution need to be like minimum or for all?
Any solution. No. Yes. Means which will mean, look at the covering edges. So suppose f is a covering edges. So edge of f, cardinality of edge of f is at least 1 by alpha times E of g. This is what I mean. Alpha fraction. No. Alpha. Alpha times Eg, because alpha could be half, 1/3, 1/4. This is what I mean.
So in feedback vertex, try to target the triangles.
Hmm?
Any circle.
Is that true, Abhishek? Is this statement true for feedback vertexes? Can I say it's alpha covering for some alpha constant, like 1/3, 1/4, 1/5, 100? 1/4. Why? No, it's not true. Take a big cycle. Take a cycle of length n. Right? Like there exists a field. Like I said, for every solution this should be true. So only 2 edges. There are so many edges. So there cannot be a constant fraction. So in general, this is not true. Yeah. So we'll get there. Okay. But we will see that on pi, it's called alpha covering if I should write if for all g, for all x subset of Eg, okay, x is a solution in this, okay. Now we will not say this. What we will say, not for all g, we will define the notion of if for all g, right, reduced g will have this property, and there will be notion of reduced g, right. There will be some applied. So given a graph g, I will give you a reduced g such that g comma k is an yes instance if and only if reduced g comma k is an yes instance. But it may not be a kernel. It will be certain pre-processing which I will do, and then this statement will be true. But we'll get there some point of time.
It can be good, but it can be.
It may be better. 99.99% it will not be. Right? Okay. So now for feedback vertex set, I apply for FVS, I apply your classical degree 1 rule, degree 2 rule. All of you know, I told you yesterday also, so I will not tell you today. And I want to say something. Right? Now, why am I saying this? Right? Now, this is all for this to show, this is good enough as a, so given a G, apply this and get reduced G. What is this? Given G, I applied these two reduction rule, I got reduced G. It's not a kernel. But if you can prove this already satisfy this with actually half, with alpha equal to half, this satisfy this condition. With just these rules. Okay? Yes?
Why is it not a kernel?
Huh?
Why is it not a kernel? I have applied the degree 1 and degree 2 deductive rules.
And then what makes the graph G kernel for feedback vertex set?
The degree 1, degree 2 deduction rules.
That gives you a feedback vertex set kernel?
What are the rules we applied?
Degree 1 and degree 2, that's all. Will that give you a kernel for feedback vertex set?
Degree 2 rule is that if I have long path, I just sort.
If I have a degree 2 vertices, then look at the edge, delete this vertex, add an edge between its two neighbors. Will this give you a kernel? I don't think so.
If you have a forest, it's another thing. If you have a forest and you have a long path, and the internal vertices don't see anything from the feedback vertex, then you can shortcut them. Right?
Yes, that is exactly degree 2 reduction.
There should be some edge incident onto them.
Yes.
That will bound the number of edges that come out of this feedback vertex.
Yes, that's why you will get half. That's why I am saying that if you look what I said, I replaced G with reduce of G, right? So, and for reduce of G, I don't need kernel. All I need is degree 1, degree 2 reduction rule, right? And I will get it. But I am not going to go there. We'll go there some other day. Okay? When we do randomization, we'll go there. But just do remember. So, what I'm trying to capture by this is that actually feedback vertex set is a problem of roughly covering half the edges and something else maybe, but it is also a problem of covering half the edges. Vertex cover is a problem of covering all the edges, and feedback vertex set is a problem of covering all the edges, sorry, half the edges. Now, so in vertex cover, what is a good primitive? What is a good primitive? Is that if a vertex of highest degree is there, right, then it looks like that it should be good for the solution. If there is a vertex of high degree, for vertex cover, it looks like branching on them or looking at them is a good idea. For example, what I mean by this, look, okay, so let's do a vertex cover example, okay. So, this is a vertex cover, okay. Now and for vertex cover I have applied no rules, okay. For vertex cover I will apply no rules. For feedback vertex set I will apply my reduced G. So for now I write down V1, V2, Vn such that degree of V1 is greater than or equal to degree of V2 greater than or equal to degree of Vn. Okay. My claim. Can I say something about first k vertices? Can I say, suppose this is set X or say H is first k high degree vertices. Or maybe we'll see, we need k or 2k or whatever, okay? Okay. Some question mark k degree high vertices. I want to claim that if C is a vertex cover of size at most k, then C intersection H is non-empty, is not equal to empty set. I want to say this. I want to prove this. What I want to say that look, if I look at high degree vertices and then maybe 2k or k, let's see what happens with k. Suppose it does not. So the bad, if it is does, then there is nothing to worry about. Suppose it doesn't. So here is your H first some question mark times k vertices, and here is your solution C, which is disjoint from this. And how many edges does it cover? What is the summation of degree of these guys? M, 2m. And this guy also sums to degree 2m. Is it possible? Let's write down now. Summation V in Vg, right? Degree of V. Now this is equal to V in H summation degree V plus V in Vg minus H degree V. Okay, let's see. Now what is the property of this? Clearly here is a C. So what is the degree of, what is the summation of degree of C? If I look at a vertex cover and I sum its degree, what is it? Is it? No. It is at least m. It cannot be twice m because there could be right. So I only count this. I am not counting this, but I can definitely say this is greater than or equal to m. So this is also greater than or equal to m because they are higher degree, because they appear before and their sum of degree is more than this. So all I need is, let's say, k plus 1. No. Let h be first, k plus 1, size k. Why? Look, first k guys gives me m. First k guys gives me m. And the k plus 1th guy will give me some extra degree. So this is strictly more than m. And this is equal to m. But this is equal to 2m, no? And how can 2m be strictly more than 2m? This is not possible. It means first k plus 1 vertices of high degree must contain some vertex from the vertex cover. So this is a very good heuristic, no? If I pick lot of vertices of high degree, then you cannot. And why it is true? Because look, they all need to cover lots of edges, right? So if you completely ignore lots of high degree vertices, there is no way you can cover all the edges. This is all that it says if you look at it. Now if I start to look from this perspective and try to design an algorithm for feedback vertex set, right? Because there we do not have guarantee that I have to cover all the edges, but I still have to cover a good fraction of edges, right? So I don't need k plus 1, maybe I need too much so that this fraction can compensate. Oh, you are too much. Oh, this fraction is also too much. This fraction is also too much. You understand what I am saying? So look, what I am saying to you, look at this. Look at any alpha covering problem. Any alpha covering problem. Suppose, then I claim to you, then if you pick first alpha plus 1 into k vertices, sorry, 1 by, why are people calling me? Okay, so here's my claim. What is the claim? Here's a claim. And alpha is less than or equal to 1, so it's a fraction, some constant fraction. It could be some function of k also, but then we will have to choose. And let's try to prove this, what happens. Okay, so our claim is, how do we achieve this? Let's not worry about it. All I am saying is that if I have a problem which is alpha covering, then I have some amazing branching algorithm. What is a branching algorithm? Here is the claim. Okay, let v1, v2, vn be the vertices ordered in non-decreasing or non-increasing, non-decreasing or non-increasing, non-increasing, ordered in non-increasing way with respect to degree. That is, degree of v1 is greater than or equal to degree of v2. Okay, so this is it. Okay, and this is an alpha covering problem. Okay, this is an alpha covering problem. Okay, so now I can write it to m equal to summation degree v in vg. Okay, we will come up with so I want to say that let h be we will see some function of 1 over alpha k vertices. We will fix what is this, yes, right? V in Vg plus, so now I will do as I did before, V in Vg, sorry, V in H degree V, okay, and what plus summation V in Vg minus H degree V, right? And what you know about this? What do you know about this? This contains my solution. This contains my solution. So they must be covering how many fraction of edges? Alpha m fraction of edges. Alpha m fraction of edges. All I need to make sure that, look, here it is 2m. All I need to make sure that, suppose, let's say beta k, what is it? What I have to show here, I know that if there are beta, like every k vertex will cover how much edges? Beta m, alpha m edges. So all I have to show that here it covers how many edges? Beta alpha m edges. Beta is some integer z, positive, natural, whatever. Okay. So look at first k vertex here. That will cover how many edges? Alpha m edges, because the vertices which are even lower degree, they in together covers alpha m edges. Then the guys which have higher degree will definitely cover alpha m edges. So if there are beta such partitions, like first alpha, first k vertex will cover alpha m edges, next k vertices will cover alpha m edges. So if there are some beta such partition, then they will cover beta times alpha m edges. So now what we have? Beta alpha m plus alpha m, all I need this to be more than 2 to get a contradiction, right? To get a contradiction, all I need is this to be greater than equal to 2m. That's it. So m goes away. So what do we get? Beta is more than, all I had to choose is 1 plus alpha. That's it. So what does it imply? And look, it's only a function of alpha, right? So if alpha is constant, I will say what I'm saying. Hey, look at large block. First alpha, like first 2 into 1 plus alpha into k plus 1 vertices. One of these vertex must go into the solution. So branch, right? I can branch on first, right? So what does this imply? This implies there exists an optimum solution that intersects H. So what is the running time of this algorithm? The running time of this algorithm will be H power k. Agreed? So H power k. So that's it. Fine. Whatever. Now let's try to prove for alpha is half. Right? That is what I will like to prove, and maybe then we'll get it. So what is a reduced G? Reduced G means no degree 1 vertex and no degree 1 vertex, no degree 2 vertices, right? Otherwise we would have short circuited it. Now look at any solution, in particular solution of size at most k, it doesn't matter. Look at any feedback vertex set and look at any forest. Okay? Okay. Now notice every leaf contributes how many edges? Its degree is 3 in graph. So every layer contributes 2 edges. Contributes at least how many edges? 1 edges? 1 edges. How many vertices are here? Suppose it is n minus mod f. I am going to show to you that for every edge here, look, if I show, look at every leaf and look at a degree 3 vertex. Degree 3 vertex is bounded by leaves, right? And every leaf is contributing to 2 edges. So he is able to compensate for degree 3 vertices, right? So now I distribute. This degree 2 vertex says, okay, take my 1 extra edge, I go and give it to degree 3 vertices. Now what did you see? Every vertex has at least 1 edge going up, right? So number of edges here is proportional to the number, like n minus 1. So at least half the edges, because there could be some more edges here. So at least half the edges of my graph is incident to vertices of FPS. Okay? So this is why alpha equal to half. Please remember. Okay? So now I set alpha equal to half. So what will be this? Is it correct? Huh? This is wrong? So did I did something wrong here? I didn't get. I wanted to take beta common because this is what we wanted to bound, no? So I wanted a, okay, so what are we saying? Can you, okay, so you are right. So I take first common beta. So then we will get beta plus 1 is at least 2 over alpha. That implies beta has to be equal to 2 over alpha minus 1. Is that what you're saying? I wanted beta, right? Because I wanted number of blocks. But alpha is function of, alpha is half for us. So it is 4. So this is equal to 3. For FVS, beta is 3. Okay. So now what does this gives us? 3k power k algorithm. So what is it? I apply degree 1, degree 2 reduction rule. I look at high degree vertices, at most 3k of them. I know one of them must go into the solution. So I branch and I keep doing this. So this algorithm runs in time how much? K power k. Okay. But this is a very general framework. It has nothing to do with, FVS, right? If I had an alpha covering problem, right, then based on that alpha, I can get an algorithm. And we will show to you that every planar F deletion is an alpha covering problem. Okay? So that's a goal eventually to show. Okay, so what is given in the book is just instantiation of that algorithm for feedback vertex set. And this is my algorithm. So I remember this is something which I designed in my PhD thesis. Like among 12 algorithms for feedback vertex set which I designed, this was one of them. It was unpublishable in those days because it was bad running time. But it got published in 2012 in a very different format. Why? Notice, what is the beautiful thing about this is now. So suppose I did this, pick a random edge. What is the probability that we will pick an edge from here? What is the probability of picking that edge? Half, because half the edges are good. So I picked, with probability half, I picked up this edge. With probability half, I pick one of these vertices and decide to put into the feedback vertex set. So what is the probability that I would have picked up a vertex in the feedback vertex set is 1 over 4. 3 times I will get 1 to the power 4 to the power k algorithm. It is a polytime algorithm, so I have to repeat it 4 to the power k time to get some constant factor approximation, which we will do tomorrow in more details. Okay, so this is why this is good, and this is a deterministic version of this. Okay, and there is a even smarter way of doing deterministic version of this using some bucketing trick which will give you C power k algorithm, but I will not do that. Okay. Okay, all good? So I gave you a 3k power k algorithm for feedback vertex set. Okay, so now let's continue our journey with feedback vertex set. So Pratibha was saying something when we started and I said not now. Okay, so what was he saying? Let G be a graph such that delta of G is at least 3. Then G has a cycle of length at most 2 log n plus 1 main fact plus 1 and can be found in polytime. Does everybody know the proof for this? It's a simple graph theorem, there's nothing to do with algorithm. Okay, so the idea is very simple. Now I can. So you do BFS, right? At any point of time, either I am doing a BFS, okay, at some vertex. sorted property of BFS, all the edges are just here. So either when I'm looking at it, it already has a neighbor here, then I'll get a shorter cycle. But till when can I continue going like this? Huh? Up to log n length, because every time the number of vertices are increasing by factor 2, right? So 2 to the power log n time will already reach n. Fine, right? So at least at the log n depth I will find an edge across. Then if I look at the common ancestor of these guys, it will give me a cycle where no path has length more than log n and plus 1. And the reason you can get plus 1 off, because the first time you do start with 3 vertex, not with 2 vertex, because first it has degree 3, so actually there are 3 and then you do this. So actually you can get rid of 1 plus 1, but that doesn't matter. Okay, so this is how you can prove. Okay, so what is the running time of this algorithm? If I use this lemma, then what is the running time of this algorithm? Right? So now I do not have, I have a bound on the cycle which I can find. So rather than finding any cycle, I find shortest cycle, which I can do in polynomial time, and I am guaranteed because of this lemma that the length. So I will say the running time of this algorithm is going to be girth of g to the power k, where girth of g is the length of the shortest cycle. Agreed? And what does lemma tells us? That the girth of g, the length of the shortest cycle, is upper bounded by 2 log n. Which is? So it is same like that, okay. I will not do this maths for you. Okay, so now you can do slightly smarter, okay, and what you can show that now I'm going to prove another lemma. Let G be a graph such that delta G is greater than or equal to 3, girth of G is greater than or equal to 7, okay. Then minimum feedback vertex set of G has size at least some constant times root, and we will figure out what this constant is, okay. Now suppose if I prove this algorithm, suppose I prove this lemma, then do we get better algorithm? If I prove this lemma for you, what will I do? Look at this algorithm, right? So either this algorithm will branch on 6 length cycle, and if the 6 length cycle does not happen, so right, it is branching, right, in 6 ways. Suddenly the length of the cycle increased, but now what I know, the feedback vertex set has size c, at least c root n because of this lemma. Then I will check, is k greater than c root n, right? K must be greater than or equal to c root n, because if k is strictly less than c root n, if k is strictly less than c root n, then answer is no, I can just stop here. Otherwise k is greater than or equal to c root n, it means n is at most k by c whole square. Now if I take this algorithm and I substitute n at some k square, what will I get? I will get some 2 log k, maybe 4 log k to the power k algorithm, which is like roughly 2 to the power big O of k log k algorithm. So if I prove this theorem, I would have done some improvements, right? Because I have to replace log n by log k to the power k, which is 2 to the power order k log k, while this is just k log k, right? So if I prove this combinatorial lemma, I will be happy, okay. So I can get an improvement if I prove this combinatorial lemma. So let's prove this combinatorial lemma. Okay, so how do we go about proving this? It's not very hard. So here is the auxiliary claim. Let T be a forest. Okay, let T be a forest and L be the set of and V less than equal to 1 and V equal to 2 be the set of vertices V less than equal to 1 be the set of vertices of degree at most 1 and degree equal to 2 respectively. Okay. Then plus okay. So let me tell you the proof strategy and then we'll see why I am trying to do this. Okay. So what I am saying is that look at this is my forest, this is my feedback vertex set and this is my forest on which I will apply this lemma, right? Now what does it say? It says, hey, look at this. Okay. Now M is a maximum matching where every vertex has degree 2. Look, it's a tree induced on V equal to 2. It means every endpoint of this matching is what? Has degree exactly equal to 2, right? So let's draw those. And these are my leaves. What can you say about leaves? Because graph has degree 3, they have at least 2 neighbors in F. And this is degree 2 vertices. So this endpoint will have one neighbor and this endpoint will have one neighbor. This endpoint will have one neighbor, could be the same neighbor for all that I care. This guy will have some other neighbor, this guy will have some other neighbor. This is my whole goal, right? Certain sort of association. I want to say that if F is too small, then by pigeonhole principle we will get a cycle of length at most 6. So that's the goal. Okay. So if I prove this, suppose I prove this for you. Okay. Now let's see how do we use it. For every leaf V, associate a pair U comma V in F, where U could be equal to V for all that I care. Okay. For every matching edge, UV, for every matching edge AB, associate AX BY in F. Okay. Now suppose and what is this? This is equal to V of t minus 4, suppose. So now what will happen? I will say if mod F square, because it could be said, right, is more than say n minus F by 4, then what can you say? There will be 2 objects which have been assigned same pair in F by pigeonhole principle. Look, I only have mod F square pairs. For a degree 2 vertex, I arbitrarily assign 2 vertices. For an edge, I know both C is in F because it's a degree 2 vertex, so I associate a pair, right. So if this is more, then by pigeonhole principle I will have two objects assigned to the same guy on the top, okay. So let's see what happens. So I have same guy which has been assigned to top. So maybe this is the guy which has been assigned to top, then I get what cycle? 4 length cycle. Maybe this is an edge, matching edge, then I get 5 length cycle. Maybe this is also edge, then I get 6 length cycle, and this will be the maximum because if any of them gets assigned to the same guy, you will get triangle or some such thing, right. So if I can prove this lemma, then I can show it has this, right. It will imply, so what happens? So this cannot happen, right. So because then we'll get a, because, so this is less than this. So mod f is less than this. You see my point? Mod f is less than equal to n minus mod f by 4. Look, if it is more than this, then we will get a 6 length cycle. If mod f squared is more than this number, then we get a 6 length cycle. But what is our assumption? The girth of the graph is at least 7. Do you get my point, I would say? So, look, if this is more, then we will get 6 length cycle. But since we do not have 6 length cycle, what is the meaning of this? Mod f square. No, did you mean that I wrote something wrong? Sorry. If it is less than this, if this is less than this, then we'll get 6 length cycle, you are right. So we can assume that mod f square is less than equal to mod n minus 4, right? Square plus f minus n is greater than equal to 0. And now if you solve for this quadratic equation, you will get some f is roughly some c root n, because square and n, right? So you can get it. Okay. So all we need is to show this lemma. Let's see how do we go about solving this. Okay. So look at graph induced on V2. So what is this? It will be some path. Now notice, I want to take a matching. So I take the first edge, second edge. When can I not take? When will I leave a vertex? If it has odd number of vertices, right? Suppose I had this, then I will pick this, but I cannot pick this edge because it's not a matching edge, right? So how many vertices of V equal to 2 will not be part of the matching? That is just because either this is, what is this? Like next to him is either degree 3 vertex, or this is, it cannot be leaf, because leaf I want, like, or what is that called? Or it will be leaf which I already count separately. Okay, maybe there will be some constant. So suppose first of all V less than equal to 1 is greater than equal to say n by 8. Okay, say n by 4, then there is nothing to prove. If we get, because I don't care what m is, this itself is larger. So let's assume that V less than equal to 1 is less than equal to n by 4. Okay, then let's see. If V is less than equal to n by 4, then the degree 3 vertices are also less than equal to n by 4, right? So I delete, okay, so V, if this is less than equal to n by 4, degree 3 vertices are also less than equal to n by 4, but that's like n by 2, and I might be missing n by 2 guys. So that's not good, okay. Let's make n by 8, I don't know, I mean some constant will work. So if this is less than equal to n by 2, n by 8 is correct. Otherwise, V less than equal to 1 is less than equal to n by 8. It means degree 3 vertices is also less than equal to n by 8. Okay. is less than equal to right, is also less than equal to n by 8. So total number of vertices which this guy will, total number of vertices which is not part of anything is n by 4, and maybe you will lose n by 4 from here. So at least in this case you will get n by 2 size matching, which is fine. I mean, so definitely this is correct, right? You can do some computation and get it like n by 4. I mean, I don't remember exactly, but all I'm trying to tell you is that number of vertices with degree 1 and the matching on degree 2 vertices are too large, like they are fraction of n, and hence we get such a bound. Okay. So let's meet at 2.